So our problem now will be a closed pressure vessel. On that closed pressure vessel, which is a cylinder, we have an applied external load which is unknown. As you read the problem statement, there are two strain gauges, one in the vertical direction, which is going to read minus 250 microns, and one in the horizontal direction, which is going to read plus 900 microns. Let's kind of capture some of the information above. The thickness of the tank is 0.5 inches. The outer radius is 24 inches. The inner radius is going to be 23.5 inches, and the mean radius would be 23.75 inches. And we'll also remember that E is 29,000 and Poisson's ratio is 0.3. So we're asked to find two things, both the pressure inside and also the magnitude of the applied external load. And although we're not going to deal with it, we have a compressive external load, so we actually have to also deal with buckling, which is something we get into in the last few weeks of the course. So again, here we'll neglect any effect of buckling. So let's come down here and redraw with some axes on. We'll put X along the longitudinal axis, Y in the hoop direction. I'm going to call that G1 and G2. And so all we're going to do is talk about the strain state and the stress state. Quite a bit that we do know about this. Tank in the hoop direction, it's going to be G2, we'll call it. Again, that has a value from the problem statement. G1 also has a value. It's going to be negative here in just a minute. I'm going to draw the arrow in tension. Right, as we move forward, right, in the end, this is going to end up being minus 250 times 10 to the minus 6. Well, this one is going to equal plus 900 times 10 to the minus 6. Now the stress state, we have a pressure vessel and a concentric axial load. So in the hoop direction, we've got sigma hoop. Right? In the longitudinal direction, we're going to have sigma hoop over 2, which is the sigma longitudinal. It's going to be in tension. And we'll also have negative P over A, where the P we're talking about here is the purple P, right? The applied external load. So these two pictures are extremely valuable. We've got the initial strain state, the initial stress state. There's unknowns that are littered across them, but we can relate these to each other, and we're just going to use 3D Hooke's law. So strain in the x direction is equal to sigma xx over E minus Poisson's ratio of sigma yy. Right, sigma zz is equal to 0. We have a plane stress problem for a pressure vessel. And so we're going to do this twice. We're going to use the strain in the x direction equation and also the strain in the y direction equation. And then all we do is just plug in what we know from above. So this is going to be sigma yy. Up here we're dealing with the equation for sigma xx. This is eventually, right, is going to be epsilon yy, and here is going to be epsilon xx. Right, just keeping in mind our coordinate system right there. So all we're going to do is just plug those into both equations. We end up with an equation that has G2 in it relating to the stresses x and y, also strain yy related to stresses x and y. Right, to help ourselves with a little bit of math, we're going to take equation 2, we're going to multiply it by Poisson's ratio, and just add those two together. And so math-wise, we end up with an equation that has G1, G2, and only sigma hoop in it. So that'll be our unknown that we're about to solve for here. Kind of looking back above, you see that we've got P over A. Up here we have, again, the same P over A, but with a negative sign. And as we multiply by Poisson's ratio, those whole terms cancel out. So just go ahead and solve this, then just combining sigma hoop, and now we've got our sigma hoop equation. And so we would just use everything that we know from above, and we're going to end up with 26.3 KSI. All right, not to make light of any of the units that are involved here, but obviously units police needs to come out. The only thing we have units on is going to be E. That's a unitless number, unitless number, unitless number. So there we have our answer for the hoop stress. And then we can relate that to the pressure inside the tank. Sigma hoop is equal to PR over T, so we can just go ahead and solve that for the pressure. So that's going to be sigma hoop times the thickness over R mean. And so you're going to end up using 23.75. And so if you calculate that, we've got just over 550 psi. So the last thing to do is solve for the applied external load P, right? The big P, the applied P. So I'm going to scroll right back up here. And you can use either equation 1 or 2, but we're going to use this one right here. We'll use equation 1. And again, what we're interested in is that guy right there, right? That's the applied external P. So we're going to end up using equation 1, and all we're going to do is just plug in the known value for sigma hoop. So if we just rewrite that equation, E times G2 is equal to sigma hoop minus Poisson's ratio sigma hoop over 2 plus Poisson's ratio. I'm going to go ahead and change colors here, right? That's the purple P, the applied external load. So there's going to be our one equation and one unknown. And so it's a little bit of math to go ahead and solve for this. But if you do it, you'll end up with an equation for the applied external load, which would be E times G2 minus the quantity 1 minus Poisson over 2 times sigma hoop. And that whole thing is going to be multiplied by A over Poisson's ratio. So all you have just say a little bit of math to get through to get there, and solving for it, we'd have 933.3 kips would be the applied external load. And again, we're neglecting buckling here or any consideration of buckling.